get through most of it, okay? So again, I mentioned chapter 2, right? Chemistry. The reason why we talk about this chapter is because that's the first, most simplest, smallest foundation of the levels of organization, right? We talk about the levels of organization, and the chemical levels where we first start at, so we need to somewhat of chemistry, right? Okay, so when we look at chemistry, we know, again, biological organism contains chemistry. That's the foundational thing. Any of your behavioral reactions, any of your functional reactions, for example, all are because of chemistry, right? And so, as I mentioned, we're going to discuss a little bit of basic chemistry. And for those that are somewhat familiar with it, this might be very much repetitive. But for those that haven't visited chemistry in a while, this might be a new or newer concept for you to grasp, right? And then we'll talk about biochemistry. Chemistry in a living organism, right? That's what biochemistry basically is, right? We'll talk about that in part B. All right. So even before we talk about chemistry, we've got to discuss really, physics, right? Because this is really physical matter. This is really physical properties per se. And matter is where we first start at, right? Definition of matter. Anything that has mass occupies space, right? Has mass and occupies space. Matter, again, can be seen, smelt, felt, or measured, right? Weight is mass plus gravity, right? When you add mass and you add the effects of gravity, which is a natural process in the universe, including in the Earth, then that would be considered weight. Okay? Again, we're talking about just a basic property of physics, right? So we know that matter exists in 3 states: solid, liquid, gas. If you know a little bit about physics, there's actually a 4th state, but the majority of stuff exists in one of these 3, or can switch from one of these 3, right, back and forth. Like, for example, this has the capability of switching back and forth between solid, liquid, and gas, in fact. Solid in the form of ice, liquid in the form of liquid water, gas in the form of vapor. Like when you boil water, right? Vapor comes off, that's the gas state. Okay? All right, so what is energy? Textbook definition, right? Capacity to do work, or otherwise known as putting matter into motion, right? Taking that matter and putting it into motion, doing something with it, right? Energy has a really unique capability in the fact that it does not have mass, it doesn't take up space, but in fact still does exist. Because we know we need it, we know we use it. We've already talked about ATP as the chemical that holds, or the molecule that holds energy. We can measure it, we know it exists, even though it doesn't have mass, right? So, not only in the living organism like a human, but in fact, around the world, just a general property in the universe, greater the work is done, the more energy it uses up. That's just something that we already know, right? We figure this out. The greater the work that needs to be done, the more energy you use to do it. And that doesn't really need to even apply to the body. It can apply to many other things in life, right? Okay, so let's define these 2 words, kinetic versus potential energy. Kinetic is the energy that gets used in action, right? used energy, or energy that's getting used right now, is called kinetic, right? Energy. Now, when that energy doesn't get used, we can store it or we can keep it until we need to use it, and that is called potential energy, or AKA inactive energy. And in fact, when we see this molecule there, that molecule is actually a molecule that stores the energy, right? In a potential form. When we use it, we actually take away one of these P's, and a P in chemistry, if you don't know what that is phosphorus, right? We break the bond, basically. And when we break the bond, energy gets released. And that energy now is freed from its storage and now can be used. Does that make sense to you? Right? That's how that works. Now we can do the same thing and come back, and when we bond phosphorus back to the original molecule and becomes ATP, we store energy again. Okay? Okay, so there's different forms of energy. Here are the four major ways we form energy and how we store it sometimes. Chemical energy, we just talked about this right here, and that's a chemical. That's a chemical, and in fact that chemical is stored as chemical energy, right? Electrical energy, right? Particles that are getting charged, that have energy, that move from one place to another. That's electrical energy. All of your electrical components at your house, the computer right now, the projector, it's all electrical energy. Mechanical energy, that's the energy in movement, right? So that's, for example, like your car, when it moves up and down, when the wheels turn, when the transmission turns. That's all mechanical energy. And then electromagnetic energy, also known as radiant energy. Those particles travel in waves. All of those are considered electromagnetic energy. Heat is one of them. Visible light, UV rays, X-rays, gamma rays, all considered electromagnetic energy. Okay? Now, we're not going to go any further than this, but we are going to have to understand, okay, these are the forms of energy, because we talk about energy transferring from one type of energy to another. Okay? All right. All right, so on to elements, atoms and elements. And again, bear with me here. We build this up, so we'll get to a point where it's all going to tie in, right? We know that all matter is made up of elements, right? Elements are things, substances, cannot be broken down into simpler things by chemical methods we would do, right? And that's not 100% true, because in chemistry you can break stuff down even further, but for our purposes, an element stays as an element, right? At least for right now. There are four elements that make up most of your body. That is carbon, oxygen, hydrogen, and nitrogen, right? All right, abbreviations for those elements, right? We've got 9 other elements that make up the other rest of the 100% pretty much, and there's 11 elements that make up a really, really small amount, Those are your trace minerals kind of thing. Most of us are very familiar with a periodic table. We're gonna look at a periodic table. We're not gonna study a periodic table. That's in chemistry. It's in chemistry 1, basic chemistry 1, general chemistry 1. Now we know that elements have a composition, right? Yes, we can't break them down any further, but we know that they're made up of things, right? Those little things, to use that word, right, are called atoms, right? We could consider them building blocks for each element. That's what we use to create an element. Not we create, but, you know, nature creates elements. What we know to be the atomic symbol is that letter to represent a certain element. There's a table in the book that has all the elements. We're not going to need to study every single element and know its abbreviation, but just the ones that are most popular for what we're going to discuss later on or throughout the semester. The C's, the O, the H, the N, the K, right? Potassium, Na, sodium. Okay. All right, so let's talk about these atoms, right? Atoms are composed of these particles, the following three, right? Protons, neutrons, and electrons, right? And they're unique in the fact that each one of them has a charge or an attraction to another particle, and one of them has no charge or no attraction. Okay, so which one carries which attraction, right? Protons, positive charge, neutrons, negative charge, neutrons, no charge, and electrons, negative charge. Okay. So if you're an atom and you're positive, you're a proton, and you're an atom and you're negative and you're an electron, there's always going to be attractions to these. They're always going to try to touch each other, basically, attract to each other. And they never do, in fact, but they pull themselves close together in that attraction. Electrons have no charge, so they don't have an attraction in that way. The number of positive protons is balanced by a number of negative electrons in an element or in an atom. And that basically neutralizes, or there's a net zero attraction in most atoms in nature. Okay? Where the protons are found and where the neutrons are found is in a place we call the nucleus, or the center of an atom. The electrons are found outside or orbiting around the nucleus. Okay? So again, if I draw, say, several protons and neutrons, and that would be the nucleus, orbiting out, getting attracted would be those electrons. That's what we mean by an orbit, or an orbit, right? And in fact, in chemistry, we use these visual models to describe or to look at how this is put together. We call this the planetary model and the orbital model. Okay, so let's break into groups, right? Active learning. Okay, 3 minutes summarizing what you read with your group members or whatever, and then clearing up any confusion that you have from where we started right now to this point. Okay, I'll start right now. All right. Here. Okay, so when we look at elements, we can define them based on how many protons, neutrons, and electrons we have. And in fact, that's what you see here. If you'll notice at the bottom here, these are 3 different elements, and you notice that they're already naming or listing per se the number of protons, electrons, neutrons, right? Because the 1, 2, and 3 mean how many particles of protons they have, electrons and neutrons. And you'll notice that there's always the same number of protons and electrons because they balance each other out, right? Now, what do you notice is the difference between hydrogen, helium, and lithium as far as their subatomic particles? What? The amount of neutrons, right? The neutrons are starting to change. Does that make sense? So depending on how many neutrons we find, then we have named an element based on that. Does that make sense? Right? That's really how the periodic table is all put together. Many scientists, many chemists throughout the years and years and years find these new elements. And in fact, I think it was a year or 2 ago, they already defined another 5. So an old periodic table, they all have to be, those elements have to be added to the periodic table. So they can continue to do this. They continue to find this even now. So it's, the periodic table is not the end all be all quite yet. They're adding, in fact, more elements because they find them. The atomic number, right? It's the number of protons in a nucleus. Just how many protons does it have? That's the number there, right? The mass number, when we talk about the mass number, it's the total number of protons and neutrons in the nucleus. Now here's a really interesting phenomenon in nature we call an isotope. This happens when an element changes the number of neutrons it has. Okay? Same element changes the number of neutrons they have, and the number of different neutrons they have, plus or minus, is what we call an isotope. And here's an example of an isotope. Here is your hydrogen atom, your basic hydrogen atom. When it adds another neutron, or it adds a neutron to it, we have this really interesting situation occur. Or sometimes it adds 2 neutrons, and we can see this interesting situation occur as well. Now, it's very rare to have this. It's not like neutrons are just added to elements all the time. It's a rare situation, but we've mentioned it here, right? Many of the elements or atoms that add neutrons will want to, by nature, give them away and go back to their original form. The ones that do that are what we call radioisotopes. When they do this, when they go back to their stable form, when they give away the neutron, what occurs is there is energy given off. And it turns out that that energy is huge, really big. Okay? We actually can use this in medicine, and this is really based 100% on radioactivity and using that and measuring it with a device. Okay? So we can actually stick radioactive, for example, iodine in the body. And we know where iodine usually goes to, and that's the thyroid gland, because the iodine gets used to make thyroid hormone. And we can watch, we can put a device, a machine, and watch to see how the iodine is getting taken up by the thyroid, and if it gets converted into active thyroid hormone. Or we can put radioactive chemicals into the bloodstream, use a device and measure where those radioactive iodine or radioactive chemicals are going to, right? And we can actually see if, for example, if there's a clot somewhere or there's a blockage in a blood vessel. We can also shoot it through the body, and depends on what it is. Like an X-ray, we can actually catch it on the other side, and whatever it hits that's dense will show up as white, and we can actually look at what's lying underneath, like bones, right? X-rays are working this way. And that's really what we're talking about this. Okay, on to molecules, right? So molecules are defined as two or more atoms put together or bonded together. Okay? Two or more atoms bonded together. A compound is a molecule. Okay? A compound is a molecule. But the only difference is it has two or more different kinds of atoms bonded together. So below I give you two different chemicals, say that, and which one out of the two, say this is number one and this is number two, which one of the two is a molecule and which one is a compound? Which one's a molecule? The first one, right? O2. And this would be a compound. And why? Because it's two or more different atoms. You have an H and an O. We have at least two there, but we actually have three, right? Two H's and one O. That's a compound. Okay. Okay, so when we have matter, most matter can exist as a mixture. We call this a mixture, where two or more components, molecules or compounds, right, are physically intermixed. Now you might think, okay, this is your science experiment kind of thing, but in fact, in nature, it exists that way too, right? And so there's three different types of mixtures. And the reason why we talk about this is because, in fact, those three types of mixtures will occur in your body or in a human body. And that's why we discuss what is a solution, what is a colloid, and what is a suspension. To add to that, we also talk about medicine. And when we talk about medicine, they can actually exist in these forms as well. So that's why we do that here, right? So this figure in your book does a really good job of explaining what is a solution, what is a colloid, and what is a suspension, right? Now the difference is the size of the solute. And we got to talk about what a solute is and what a solution is, right? A solute is anything that's put into what we call a solution, right? Anything that we put into something else, we call that thing that we put it into a solution. The stuff we put into it a solute, right? And in fact, we just used, on the very top, we're using, let's say, just water and a solute, right? We look at the size of the solute, right? Okay? And it does different things. There's a different effect that will happen because of that. When the solute is really small, okay? They're so small size-wise and so light size-wise that it actually will stay in suspension, right? That will stay in the solution. And we call this a solution, right? All these little tiny dots in the beaker represent all those solutes. Suspended in the water, which means they don't fall out, which means they don't go out to the bottom or stay at the top. They're still there and they stay there. And it doesn't matter if you shake it or you leave it there, it'll stay like that because they're so small and so light. Remember that if this is water, water is also what? A compound, right? So it's chemistry too. So the water molecules and the little solutes are separate, and they keep them separate and they keep them in the whole solution, in the whole beaker. Now, if they're a little bit bigger, okay, they don't settle out either, but they actually form and hold water in this weird, interesting way, like this, right? Everybody knows what Jell-O is, right? Jell-O is mostly made up of water, by the way. Gelatin is the other, is the solute. And then we've got a little bit of sugar, and of course we've got like coloring and some flavoring, right? That's really what Jell-O is all about. Nothing complex about it. But it's a colloid. We call it a colloid. And the reason why is because it holds water in this really interesting way, and it actually forms gels like this, right? This jelly-like thing. Now we know that temperature works against it sometimes. So if you take Jell-O and then you kind of leave it out, right? It starts to kind of fall apart, right? It'll do that. That's why we have to keep it in the fridge, or that's actually how we have to prepare it first, right? We prepare it, then we put it in the fridge, and then it hardens after a while. Because temperature also affects that too. And finally, a suspension. The solutes are much, much bigger. And because they're much, much bigger, when you stop moving let's say the water, those solutes will fall out. They'll settle to the bottom because they're so big and so heavy, right? And this happens in your body with blood. So let me ask you, what prevents the solutes from falling out in your body? What particular thing helps blood stay like this? Because this is unsettled blood. And then if we took a tube like this and we sat it there on the table for, let's say, 15, 20, 30 minutes, it'll start to look like this. You see all the red blood cells fall like this? And they collect at the very bottom. Then you have all the solution, which we call plasma, because there's other things in there, but it's water too. So why doesn't this happen in our body? Because it doesn't happen this way. It stays like this all the time. Because?
Constantly in motion.
Because?
Because the heart's pumping it for you.
Because the heart is pumping the blood and creating pressure that's pushing the blood through and consistently mixing it, and it stays like this. Yeah, very good. So what happens when patients have heart issues, for example, like cardiac tamponade, the electrical output's not working, so the heart's not beating as fast. Blood can have the capability of clotting in places. Yeah. And strokes can occur. Yeah, things like that. Does that make sense? That's kind of why we're talking about this. This is why. Okay. Go past all that because we just kind of, let's get into chemical bonds, right? Chemical bonds. Chemical bonds are energy relationships between electrons of other atoms. Okay? So So we use that keyword energy relationship to talk about how atoms, electrons from one atom and electrons from another atom are sometimes attracted to each other. That's the relationship we're talking about. And in fact, a chemical bond is not a physical structure. Even though we see lines to represent them, it's not a physical structure. Okay? It's just a relationship. It's an interaction between one atom and another one. So when we look at an atom, we know that the electrons, remember, go around the center, right? That around area, we call that an electron shell. It's not really a shell, but it kind of looks like a shell. Right? Now there's sometimes more than one shell, which means that some electrons are closer to the nucleus than other electrons, because those other electrons are further out. And so we create these levels of electrons that are going further and further out, depending on what atom it is and how many electrons it has. Okay? Here's the rule with electron shells, right? The first one can only hold 2 electrons. The second one holds 8 electrons. The third one can hold 18. And if it's a 4 shell, it can hold another 18, fifth, on and on and on. The outermost one of any atom is called the valence shell. The electrons that are found there are the ones that are involved in chemical bonds or chemical reactions. And only those. Okay? Only those. So we use this rule. It's called the octet rule, but the rule of 8. And the rule of 8 says that you want to have 8 electrons in your valence shell, and if you don't have them, if you don't have a complete 8, that you're always going to try to attract other atoms that have electrons so you could share them or sometimes steal them to make your 8. Because in nature, 8 means you're stable, you're complete. And that's what every atom is desiring to do. Now, some atoms already have 8 there, or they're totally fine set up that way, and they're already stable, right? And because of which, they don't interact with other atoms. Okay? So instead of talking through it, I want to show you how that works, right? So here is actually helium. We know what helium gets used for. It's a gas, right? Helium, you can blow up balloons and floats. It's less dense than air, so that it'll push up whatever it's contained in, right? Like a balloon. And you see that it has 2 protons, 2 neutrons, 2 electrons. Remember the first shell holds how many? 2. It only has 2 electrons, so it only has 1 shell. Does that make sense? There's no extra shells here. That doesn't exist in helium by nature, right? So it's totally fine set up this way. It doesn't want to be messed with. It doesn't want to be touched. It is considered stable. Does that make sense? Okay? Neon is the same thing. 10 protons, 10 neutrons, 10 electrons. Okay? Its first shell is what? 2. Its next shell, the second one, can hold a maximum of how many? 2, 4, 6, 8. Right? So this is 2 and this is 8. It's got 10 electrons. It's stable, right? It's also considered stable. It does not want to be messed with. It doesn't really interact with other atoms. It's totally fine by itself. Does that make sense? okay? So some of them are like this, but the other ones are not. I want you to notice all four of them. Hydrogen, carbon, oxygen, and sodium. All of which get used in a living organism frequently, right? We're dependent on all of these here, okay? Now notice hydrogen. It only has one in its first shell, so how many does it need to make to become stable in its first shell? One more. If it had one more, it would be stable, and that's really the purpose of looking at this, right? It becomes stable. Okay, so bear with me. We'll get to that in a second. Look at carbon. It has how many in its first shell? Okay, that's good. Second shell? 4. How many do you think it needs to become stable? 4 more, right? So if it had 4 more, it would be stable, right? Oxygen is 2. It has 6. So we can just kind of speed this up. It needs 2 more to become 8, right? Sodium, 2, 8, and then 1 electron. It needs a lot to become stable in its shell. But we have a special thing that happens with sodium, and we'll get to that. Continue on with the types of bonds, right? So what we're going to talk about here is the ionic bonds, right? Or ionic bonding. Ionic bonds, and the reason why we call it ionic bonds, because the first word is ions, right? So we got to define what an ion is, right? That's why we're defining it right now. Because if you understand what an ion is, then you understand what an ionic bond is, right? So what is an ion? An ion is an atom, okay, that either gains or loses an electron and becomes what we call charged, okay? It gains or loses an electron. Now, we don't lose protons. Atoms don't lose protons. Sometimes they gain neutrons and they lose them like an isotope. But electrons can be lost and gained depending on what the nature of the atom, okay? Not every single one of them does it. Some of them do it. And when they gain or lose an electron, the result, they become an ion, okay? What's occurring, right? We're transferring one electron from one atom to another in the outer valence shell. Remember, we know what a valence shell is, hopefully, right? You know, that's the one that's the electrons that are the furthest out from the center of the atom that we call a nucleus, right? Talking about those. They'll be lost, and another atom will gain them, right? So somebody has to lose and somebody has to win, right? Somebody has to gain one and somebody has to lose it. Okay? Does that make sense? Now, both of them, one that gains and one that loses, both of them are called ions. Okay? Now, we have a special name for the one that loses an electron. We call that an anion. And the one that gains it, we call that a cation. Anion, cation. Okay.
Aren't metals anions and non-metals are
Yes. Yes, you can classify them as, yeah, metal, non-metal. Yeah, if you want to use them in that context. Yeah, absolutely. We've had a chemistry class before. Yeah. So when you lose an electron, you become more positive. And when you gain an electron, you become more negative because an electron has a negative charge. Does that make sense? So you get more negative, you get more negatives, more negative charges, you become more negative. Right? When we do that, when those two atoms do that at the same time, they actually end up attracting to each other because now they have a charge to them. And that charge creates the ionic bond that we have. So let's look at the example that you have in your book. because the figures tell much more than I could, speak, right? Here is this one. Remember I told you I'd come back to it, right? Here's sodium, coming back to it. Remember we talked about, here's the 2 there, here's the 8 there, and then there's the 1 on the outer shell, right? 1 electron. And that it needs a lot of electrons to become a stable full shell, right? So instead of gaining a lot of electrons, because they would have to have a lot of work to go find all their atoms to say, hey, can I have your electron, can I have your electron, can I have your electron? And there's a lot that is needed. The best way, the most efficient way is to actually just give the electron away, like it's doing here in the dotted line. Let me just give it away. And in fact, if I gave it away, the result is I become stable. Oops, sorry. Does that make sense? Because the electron's gone, so the shell is gone, right? The shell just basically is a way to describe the electron moving. It's just when the electron's gone, there's nothing there, right? So now I'm stable. There's a complete 2 and 8. There's no other extra one waiting for us to become a full shell. Go ahead, Jen.
You said that the valence shell is the one that's the outermost.
That's
So,
correct.
If it gets more than 2, what is the center ones? Are they just shells?
So the first shell can only occupy 2 by rule. If it adds an extra one, say it adds a third one, then that occupies a next shell over, and that one's open, right? And if all 8 are filled there, then the next shell is open.
But would all the extra ones outside of the first one be valence shells, or is it only just?
No, only the outside one, the one that's furthest outside. Now in this one now, the stable one, this is now your valence shell here. That's your valence electrons. Now, and if those all went away, let's just say, and we pretended it all went away, then the 2 in the middle, that's your valence shell. So it's whatever the outside shell is, whether it be the 2 or the however many rings, because there's a lot of rings. If you go down the periodic table at the very bottom, this is like 7, 8, 9 shells. That's how many electrons they have. It's a huge, huge atom. Yeah. Does that make sense to you? We see what we're seeing? Stable. It's stable. It likes to be in this state. It's like, I'm great. Believe it or not, if it lost an electron, it's good. It prefers this one. Now it interacts with another atom in nature we call chlorine. And chlorine so happens to be missing 1 electron by nature. Does that make sense? To become complete. If it is missing 1 electron, it is a perfect pair with sodium, because sodium wants to give 1 away. It doesn't want to give 2, it doesn't want to give 3, just 1. And chlorine just wants 1, okay? And so because of that, they frequently interact with each other. The electron gets given away by sodium. Chlorine accepts it like it does here, becomes stable, and they have a negative charge and a positive charge, right? We call these ions. Cation and anion, basically, right? Cation is the positive, anion is the negative. And because they have a charge like this, they actually have an attraction to each other, right? They attract to each other. And this attraction to each other is called a ionic bond. Okay, that makes sense? Lo and behold, we call that sodium chloride. That's table salt. That's your normal plain Jane table. Actually start to dissolve it, right? We have a solution again, right? Be salt water, right? Add salt, add water. Okay? So let's talk about covalent bonds, right? When you hear the word covalent bond is the key word here is sharing. Okay? Sharing. So what are we sharing? Of course, we're sharing what? Electrons, right? Now, we can share 1 electron with each other, 2 electrons, and in a rare situation, we can share 3 electrons. But that doesn't occur all that common, right? There's more double bonds and single bonds than there are triple bonds, called a triple bond. Okay? By sharing an electron, the shell is partially filled, and that still checks the box of it being stable. Does that make sense? Because you're actually borrowing the electron in time and giving it back and borrowing and giving it back, so you become more somewhat stable. You are stable, in fact. And there's 2 different types of covalent bonds: polar and nonpolar covalent bonds, or relationships where they share electrons. So I want you to look at this figure here, right? Figure 2.7a, and we're looking at a covalent bond. We haven't figured out yet if it's polar covalent or nonpolar covalent. We just know it's covalent. And I want you to notice hydrogen. Now, hydrogen's our first atom in the periodic table, and it actually just has 1 proton and 1 electron. It doesn't even have neutrons, by the way. Not that that's shown there, but I'm just telling you, right? Now, since it has 1 just really wimpy electron in only 1 shell, how many do you think it needs to become stable? How many does hydrogen need to become stable? Needs 1 more, actually, right? And it needs 2, right? 2 total. Yeah, I think that's what you meant. Right? And it becomes stable. If I wrote that electron in the red there, that's a stable hydrogen atom. Does that make sense? Now look at carbon. Carbon actually has 4 in its outside shell. It needs 4 more to become 8, right? So you can't just find 1 atom with 4 electrons. It's really hard to find. But what you can find, which exists out there a lot, is a bunch of hydrogen atoms that just so happen that they need 1 to become stable, right? So we can pair 4 hydrogen atoms to carbon, and then we make chemicals like that. That's methane, by the way. This is methane gas. If you go to an oil derrick, right, they're drilling for oil or gas, they're pulling the gas, and some of that gas is trapped. Methane can be trapped in the ground, and they would burn that off. So stuff that they light on fire is basically methane gas that they're lighting. That's the chemical for it. 1 carbon atom and 4 hydrogen atoms. And this is how you would write it, right? You don't need to know, okay, this is methane or butane or isopropane or anything like that. You don't need to know that. We're not getting into that chemistry. That's for Mr. Garcia's class. We're just looking at how this works. Does that make sense to you? All right, okay?
So we don't need to have drawing anything?
You don't need to draw any chemical bonds. Now look at oxygen really quick before we kind of move on. You know that oxygen, if you just count them, is 6. They need 2 more to become 8, right? So does oxygen on this other side. Another oxygen molecule, same thing. And so they can share 4 among them. 4 among them, right? And they can form what we call a double bond. You see that double bond right there? So they're sharing 4 electrons amongst themselves, and that completes their 8, right? Because it's 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? And the same thing on the other side. That can be counted as 1, 2, 3, 4, 5, 6, 7, 8 on the other side, because they're sharing those electrons. Now it can get confusing to some students because they look at the chart and they say, okay, well, these are on that side right here and these are on that side right here. But in fact, those are going to the other atom and those are going to the other atom, and they're sharing the electron. There's a triple bond. I told you that was kind of rare, but nitrogen formed a bond. Okay. So let's define what a nonpolar and polar covalent bond is. Okay? A nonpole, keyword is pole, but this is nonpole, so it's not a pole. Covalent bond is an equal sharing. The keyword is equal sharing of electrons between the atoms. What this means is equal equal time spent around each atom. That's what that means. That's what that means by equal. Equal amount of time spent around each atom. That satisfies the stability, okay? And it's balanced. Stable means balanced, right? Or balanced means stable. And it's great. Everybody's happy they're in nonpolar covalent. Equal amount of time. That makes sense to everybody, right? Okay. Carbon dioxide is a great example of that. And in fact, there's not only just one electron, there's many electrons being shared. There's actually two double bonds from oxygen and carbon, and they are nonpolar. Now, here's the polar covalent bond, okay? They're still sharing, but it's an unequal sharing, which means an unequal amount of time is shared, the electron is getting shared by an atom versus the other one. Okay? We create poles, right? Poles. That's what poles mean. So what does a pole mean, right? So if I ask you, for example, the North Pole and the South Pole on Earth indicate what? The location of what? Two extremes of the Earth, right? Top and bottom if the Earth is staying still, right? But the two extremes on Earth, right? The reason why we use pole is because there's two extremes of electrons because one is getting shared more than the other. Okay? There's an unequal sharing. Now, why does this occur? Because sometimes, and most of the time in a polar covalent bond, one atom has many more electrons overall than the other atoms would, like here. Water is a polar molecule. Okay, it's a polar covalent molecule, which means they share the electron, but one of them shares it most of the time than it does to the other ones. Which one of the three, because this is H, this is how the bonds work, right? The line represents the relation, the bond, right? The polar covalent bond. We've got one atom of hydrogen, another atom of hydrogen, and one atom of oxygen. Which one of the three do you think is the bigger, more heavier, the one that has more electrons? Oxygen, obviously, right? Oxygen's the one that has the sharing that's unequal. It spends most of the time with the shared electron. And which electron is it? It's that one here from hydrogen. Remember, it only has one? Those two are getting shared by oxygen more than the hydrogen is sharing the other electron from the oxygen.
So this most likely happens when there's two or more atoms sharing.
Yeah, I would say so. But there are situations where it's just two atoms together, and one of them shares more than the other. Yeah. Carbon monoxide works that way too. CO, right? Carbon monoxide. Not carbon dioxide, mono, right? Monoxide. Water is so interesting in the fact that it's nonpolar, that it shares the electrons so much that we designate these little Greek symbols and this positive negative to indicate where the electrons get pulled or share most of the time with, what side of the molecule. Does that make sense? Mm-hmm. Because of which, all the electrons of the oxygen and those two that are getting shared by hydrogen get pulled in this area more than any other place in time. okay? They get pulled that way, okay? Because of that, the bond or the chemical relationship always has this angle, right? This weird angle. That's why you always see water look this way in this type of, when we write the chemical formula, and you don't see it this way. You don't see it that way, right? Like you would see CO2 or any other ones. You see it with this angle here. The reason why you see with that angle is because the electrons get pulled so much. So this figure here in the book shows you the 3 bonds, right? Okay. Talks about those 3 which don't break. The hydrogen bonds keep the foot up, and it bends the water. Do you see what I'm saying? These are the ones that are keeping the bug up on top of the water. Does that make sense to you? It does not break. Now, if we were to do that, of course, we would break the water. But you can also do this with your hand. You take water and you kind of put your hand on the very top and ever so slightly try to push down a little bit. There's a little bit of a resistance if you really pay really close attention. A little bit. If you just go like this, it's not going to, it won't work. But if you kind of push down just a little bit, it works that way. It's the same thing where you actually can put something on top of water and it'll float like a boat. Same phenomenon because hydrogen bonding works there. Okay, let's take 3 minutes. Discuss what we just talked about, which is the bonds, right? 3 bonds. Highlights of anything that you see there or any misconception, make sure that you discuss in your group, okay? All right. All right, so on to chemical reactions, right? I mean, we were talking about chemical bonding, which is a reaction, in fact, by technical standards, but we want to talk about some other reactions, right? So let's talk about a chemical equation, right? An equation is a way to understand, a way we write down how chemicals are interacting with each other, right? How they're reacting with each other, right? And in an equation, we always have a reactant and a product, right? Reactants are things that are entering the reaction, and then what happens when we interact with them? What is the result? Those are the products, okay? And we always know that there's formulas on a chemical reaction. We know that those are written in the abbreviations. That's what you see all through here, right? Some reactants and products there. And so let's talk about the 3 main reactions. There's many other reactions in chemistry, but the 3 main ones we want to talk about just to make sure that we understand these, because these are where most of our reactions are occurring in the human body with these 3 main ones, right? The first one is a synthesis reaction. Synthesis means to synthesize, means to make, right? And the way you can make in chemistry is if you take chemicals and put them together and put them together and put them together, or synthesize reactions, right? It's basically, that's very simple how you think about it, right? One of the type of synthesis reactions we're going to discuss here in this class is anabolism, right? We talked about anabolism yesterday in chapter 1, building things up. And anabolism is the building process. So I want you to look at this chemical reaction here, a chemical formula. A represents any chemical composition there, maybe it's a molecule, doesn't matter what kind of molecule. And B, the reason why we changed the letters, just to let you know, it's a different chemical, right? 2 different chemicals. And we put them in a place and we watch them to see what happens. And in fact, the product is AB, which means there's some kind of bond that forms there that holds them together. So we have a new product. That makes sense? This is synthesis. So this occurs in the body, and here's an example of how it occurs in the body, in the fact that we're taking reactants like amino acids, and we are putting them together or bonding them, in fact, or undergoing anabolism to create a long chain of amino acids, and that'll eventually become a protein. That's how proteins get made in the body. This is a simple process that you see here, but it's much more complex. But in fact, it follows that same rule where we put stuff together, we put it together, and we form these bonds. The reactions occur, and then we start to form these bigger molecules like a protein. All right? Everybody see that there? Right? It's a molecule. Okay. And in fact, this should be this, right? So we're taking this exact same thing, same reaction that we saw in anabolism, A plus B equals AB, or goes to AB. There's a bond there, or bonds, or whatever. And then we say, okay, let's just go back to the beginning. We'll take AB, and something happens to break them apart. Bonds break, let's say, and it becomes AB, right? Catabolism. So how does this occur in the human body? And that's why do we study this right now? Because in catabolism, we need to do this for glycogen breakdown. So let me walk you through this. Glycogen is a large molecule found mostly in the liver and in skeletal muscle. Okay? Notice that these little six-sided molecules are glucose molecules. Okay? It's a way to store glucose molecules in the liver and the skeletal muscle. My question is, why would you want to store glucose away? What did we learn from chapter 1 that I mentioned? For what?
Energy.
For energy. To convert that energy that when we break bonds, the bonds of glucose, we put that into what molecule? Say it louder. ATP, right? Because we use the energy that's in the bonds of glucose, and when we break them, we take the energy and we harness it, we put it into a molecule we call ATP. Right? We make energy that way. Does that make sense? So the way we store glucose so it won't react in the body is in this form that we see in glycogen. Everybody see that? It's like little branches on a tree. Okay? And the lines represent bonds, right? This is chemical bonds, right? We stick it in the liver, in a place in the liver, and we stick it in skeletal muscle. And when we need it, we can basically prune the tree. You know what I mean by pruning a tree? Right? Get little shears and cut little pieces of glucose off, or all of it if we want, if we need it all. And this is what's occurring down here. You see that there's free glucose here? We call it free glucose, but it's not bonded to each other, right? And we do this through catabolism, right? That's a series of breaking down one large molecule into smaller molecules, right? This is what's occurring here. Large molecule into smaller molecules. Then we can use that glucose molecule, break that apart even further, and then convert it into, finally, ATP. And that's what is occurring in your body. And in fact, when you eat breakfast in the morning, since we're still kind of somewhat early, we eat breakfast in the morning. And then after that breakfast, what's occurring is your body's digesting it. Some of that glucose, we're converting it into this, and we're storing it here. And throughout our morning, if we need more blood glucose, more sugar, we'll pick it off and pick it off and pick it off. And sometimes the warehouse will be empty by the time we hit, let's say, 12 o'clock, right? Or lunch, or whenever you eat, whenever you're starting to get hungry. And then we reload those up. That's what the body's doing. Okay? Now a third one we call the exchange reaction, or exchange reactions, is involving both the two reactions that we just talked about, synthesis and decomposition, building up and breaking down at the same time. So sometimes what we want to do is exchange, take molecular bonds, break them, and then put other stuff together, right? And that's what happens in an exchange reaction. If you'll notice here, AB plus C yields AC plus B if we want it to. In this example, we're wanting to do that. What we're wanting to do is take AB, the bond there, break it up, which means catabolism, right? And then we have C there, and then we want to take C and bond it to A, which means synthesis, right? And leave B by itself. This is what's occurring there. Does that make sense? You just don't see that right here on the very top. What you're seeing is that extension. That's kind of what's happening. We see catabolism there and anabolism there for an exchange reaction. Does that make sense to you? Okay, that's what we're seeing there. You can be as complex as you want. You can have two different ones and then switch them all around like you're doing here. So this is an exchange reaction. It's just a bigger one. Or you can take a big old huge molecule and then exchange all of these back and forth, back and forth, back and forth. The whole point is we want to make new things from stuff that we've taken in or we're using originally. Take reactants and make new products. Okay? Go to that, right? Energy flow. All reactions are either exergonic or endorgonic, okay? And these two discuss energy, okay, getting used or energy as a side product of a reaction, okay? Remember I told you that when we actually convert and do reactions and actually we have energy, that energy gets lost as heat, right? Many times. When in fact, in an exergonic reaction, we give off energy. Energy gets lost in that reaction. This will usually happen in a catabolic reaction where we break stuff apart, right? Catabolism is breaking stuff apart, decomposing. Or what we call an oxidative reaction, which means we transfer electrons from one to another, right? That usually loses energy. Energy gets given off. In an endorgonic reaction, we actually use up energy, or we have to put energy into the reaction for the reaction to occur. And that usually happens when we're building up things, right? Or anabolism. When we're building up things. Remember, the more work that you do, remember that property? The more work that you do, more energy you need to do it, right? So if you're building a lot of things in your body, you're building structures and more cells and stuff like that, you're going to need a ton of energy. That's why it's really important to eat when you study. That's why, I don't know if you notice this, but when you study a lot, you get what? Hungry, right? You're very hungry, in fact, because you're using a lot of energy for neuron connection, for brain development. In fact, that's what you're using. You're using a ton of energy to study, basically. And because of that, you need a ton of energy to do that, because we're building things up. Okay? In theory, all reactions are reversible. In theory, right? Theoretically, we have the capability of reversing all reactions. In reality, some reactions like to be, we put two things together and then they get bonded together, and they don't like to be unbonded, right? In reality, some of the reactions work that way. They don't like to go opposite. Now in theory, what I mean by theory is that we can actually, if we did this in a scientific experiment, we got products, we can put a lot of energy to reverse it. But in your body, a lot of times it goes one way and it doesn't go the other way, right? We have to go through another process to do that. That's what we mean by that, right? Usually the energy that it requires to go backwards is real high. And the body's very efficient. It's like an efficient machine. It doesn't want to just use energy just to use it and waste it. It's very efficient. So it will prefer to go the other way and stay that way if it costs too much to go that way. Okay? So let's talk about this, right? We call this the speed of chemical reactions, but we would also know this to be the rate of reaction. How fast or how slow a reaction goes depends on these three main things. Temperature, how many reactants you have, or we know that to be the concentration, and how big the chemicals are, the particles, right? That is a big role player. If you increase temperature, you're usually going to increase the rate of reaction or how fast a reaction works. RXN means reaction. That's a short, abbreviated version of reaction. That's usually what happens. When you increase concentration, you usually, not always, but usually increase the rate of reaction. Particle size, the smaller it is, the more it reacts, the faster it reacts, sorry. Smaller it is, the more it reacts. Okay? So we'll talk about this, catalyst, right? Catalysts increase the rate of reaction without it being changed or becoming part of the product. So it's a helper. It's an assistant. That's what a catalyst is. Okay? It's some other chemical that helps to increase the rate of reaction, make the reaction much faster. Does that make sense, right? Now, when you increase the rate of reaction, you want to increase efficiency. So you want to do it as efficient and as fast as possible, right? And the body's always going to try to do that. That's the goal of doing reactions in the body. Enzymes are biological catalysts. They are the ones that are catalysts that helps increase the rate of reaction.